Hello, welcome to the 6th pre-recorded lecture for Math 155. Today I'm going to be talking to you about eigenvectors and eigenvalues. So we've talked a bit about matrices and what they are and different operations that we can do on matrices and why they're important for solving linear systems of equations. If we want to solve population models, we need to understand what happens to the long-term behavior of our systems. So if, for example, we have a population described by a vector and we apply a matrix to it, so that's describing how the population is changing in 1 year. Well, if we keep applying that matrix to the population over and over and over and over again, then we want to know what's happening in the long term to that population. Is it growing? Is it shrinking? Is it growing in a particular direction or a particular proportion of, say, juveniles to adults? So we can do that, we can understand what's going on by looking at some special properties of our matrices, which are referred to as the eigenvalues, which are scalars, and their associated eigenvectors, which are vectors. So geometrically, what goes on with eigenvectors and eigenvalues, every time you have a vector and you apply a matrix to that vector, you are rotating it and stretching it in, if you imagine this is in 2D, you're rotating and stretching that vector in a particular way. And if you keep applying that matrix over and over and over again, you are stretching and rotating that vector ultimately towards your eigenvector. And whether you're stretching it or shrinking it depends on your eigenvalue. So when you think about eigenvalues and eigenvectors, think about the long-term behavior of systems. So it'll turn out that these are really important for understanding what goes on in that long-term behavior. Today, we're not going to be talking about the models themselves. There's a little bit of information here on this first slide about those models, but we're just going to be talking about what an eigenvector and eigenvalue actually is and how we calculate them. Okay, so let's start off by considering this example here. So we've got a matrix A, 1, 2, 3, 2, and then we've got these different vectors, U1, U2, and U3. And let's do some calculations. So what's A times U1? So this is 1, 2, 3, 2, times by U1, which is 1 minus 1. So if we calculate that, we end up with minus 1, 1, which looks kind of similar to what we had before, but this is actually minus U1. Okay, so this tells us that if we do A times by U1, we get minus U1. Okay, that's kind of interesting. What about if we do A times by U2? So we've got 1, 2, 3, 2 again, and here we've got 1 and 3 over 2. If we calculate this, we end up with 4, 6, which we can also write as 4 times by 1, 3 over 2, which is 4 times by U2. So A times by U2 is equal to 4 times U2. Okay, that's, again, quite interesting. What happens if we've got this final example, 1, 2, 3, 2, again, our matrix A times by U3. So U3 here is U1 plus U2, so that's 2 and a half. In this case, we now get the vector 3, 7. What do we know about this? Well, 3, 7, well, we could rewrite that as minus 1 minus 1, which is just minus U1, plus 4 times by 1, 3 over 2. So that's minus U1 plus 4 times by U2. So why have we picked these particular values? Well, these ones here, these first two, U1 and U2, they have these special properties that A times by that vector gives some scalar times by that vector again. These turn out to be our eigenvalues and our associated eigenvectors. And this third example here is showing that if we take our matrix and we multiply it by the sum of these two eigenvectors, we didn't know they were eigenvectors to start with, but they are eigenvectors, when we apply our matrix to them, everything is being stretched in the direction of this more larger eigenvalue. Okay, so this, if we kept on applying A to this system, ultimately, if we do A to the power of n times by u3, it's going to be very similar to, it's going to be stretched in the direction of u2, and u1 becomes negligible. And that becomes important later on. So if we just try and visualize what's going on here, if we have u1, so u1 was 1 minus 1 originally, so this is our u1. If we do A times by u1, we get minus u1. So this here is just A times by u1, which is minus u1. Okay, let's look at u2. So u2 was 1 and 3 over 2, so that looks something like this. So that's our u2. And then when we do A times by u2, we get 4 times by u2. So that's going to look something like this, something up there. So that's our A times by u2. And then if we have u3, u3 was 2.5. So u3 was something like this. And if we do A times by u3, we end up getting a vector something up here. So this is our A times by u3. So what's going on here is that as we, in the case of our u3, for example, if we keep applying our matrix A to u3, then ultimately it's going to keep getting stretched in this general direction here towards this eigenvector. Okay, so over longer periods of time, if we keep applying A to this vector, it's going to get stretched in the direction of our u2. Okay, so that's what's going on geometrically. How do we actually go about calculating our eigenvalues? So if we have a case where A times by a vector is equal to some scalar, in this case lambda, times by that vector, well, we can rewrite this as AX is equal to lambda x is just the same as AX is equal to lambda I times x, where I was just our identity matrix. Then we can rearrange this. So we can take what's on the right-hand side away from both sides, and then do some factoring. And we end up with A minus lambda I times by x is equal to 0 vector. So if we could, this matrix here is just some other matrix B. Okay, so if we could invert this matrix, then we'd get x is equal to the inverse of this, so A minus lambda I inverse times by x, times by 0, sorry, is equal to 0. So that's what if we could invert this matrix, that would mean that our vector x was equal to 0. And because this is true for any vector x, we know that this can't be true in general. Okay, so we know that x is not 0 in general, so that matrix must be singular. In other words, our matrix B, which is equal to A minus lambda I, is singular. And that means that our determinant is 0 for this matrix A minus lambda I. Here is not invertible, so this matrix is the same as this one up here, this B. This matrix, A minus lambda I, must have determinant 0, and we can use that fact to find the eigenvalues. So for a square matrix A, the scalars lambda are the eigenvalues of A if the determinant of A minus lambda I is equal to 0. And this equation here is called the characteristic equation. So the characteristic equation of our matrix A. So this will be different. It'll be a different characteristic equation for a different matrix. Okay, so let's go through an example. So we had this matrix here from before, A is equal to 1, 2, 3, 2. And we want to find the eigenvalues of this matrix. So we do the determinant of A minus lambda I. So what's that? That's the determinant of our matrix A, 1, 2, 3, 2, minus lambda times the identity matrix. So that's just minus lambda times by 1, 0, 0, 1. So if we do the algebra inside the brackets first, then we're going to end up with 1 minus lambda, 2, 3, 2 minus lambda. So all we're doing here is we're essentially taking away lambda from our main diagonal. Remember, lambda is something that we don't know, but we're trying to find out. So we want to have an equation in lambda that we can then solve for lambda. Okay, so we just work out the determinant of a 2 by 2 matrix, and we know how to do that. So we take the product of the elements on the main diagonal and subtract the elements, the product of the elements on the off diagonal. So this is just going to be equal to 1 minus lambda times by 2 minus lambda, and then subtract 2 times 3, which is just a quadratic equation. So you have lambda squared minus 3 lambda, and then minus 4. Let me simplify that. So if we want to find lambda, we just need to solve a quadratic equation. We could use the quadratic formula, or we can complete the square, or we can factorize, depending on the scenario. Here, we can just factorize this. So if we want to find the roots of this, we set it equal to 0. So we set 0 is equal to lambda squared minus 3 lambda minus 4. And you can factorize this into lambda minus 4, lambda plus 1. So that means that we can write down our two solutions to this quadratic equation, our two roots. Lambda 1 is equal to 4, or lambda 2 is equal to minus 1. Okay, so these values here are the values that would set either of those terms in the parentheses equal to 0. So either of these values, if we substitute them into our quadratic equation, lambda squared minus 3 lambda minus 4 is equal to 0, will work. So either when lambda is equal to 4 or lambda is equal to minus 1, then that equation holds. So these turn out to be our eigenvalues. So they are the solutions for our characteristic equation. So our first eigenvalue here is 4, and our second is minus 1. If you'll note, these are, if we go back to the beginning, these are the values that we got here. So we had minus 1 here. That was one of our eigenvalues. So A times by U1 was equal to minus 1 times by U1. And A times by U2 was equal to 4 times by U2. So our second eigenvalue was 4 here. Okay, so those things match up. We can now use our eigenvalues to find our eigenvectors. So each eigenvalue, as we had in this example at the beginning, we had an eigenvalue of minus 1 and an eigenvalue of 4 here. Each eigenvalue has an associated eigenvector. So minus 1 was associated with U1, so that was the eigenvector for the eigenvalue minus 1. And the eigenvector U2 is associated with the eigenvalue 4. So if we have, in general, a square n by n matrix with eigenvalues lambda 1, lambda 2, and so on up to lambda n, then we say that the eigenvector, which I'll call Vi, associated with lambda I, satisfies the equation A times by Vi is equal to lambda I times by Vi. So we could rearrange this into putting all of the terms onto the left-hand side. And this just gives us an equation of the form A minus lambda I times by the identity matrix times by Vi is equal to 0. this is the 0 vector. And this here, this is just some matrix, call this matrix M. So we're just solving a linear system of equations. If we can solve this linear system of equations, then we can work out what our eigenvectors are. Again, so let's carry on working through this example where we had A is equal to 1, 2, 3, 2. And we've already worked out that we've got our eigenvalues as being 4 and -1. So what we need to do now is we need to take each of these things one at a time and work out what our linear system of equations is, and then work out what our eigenvectors are from that. Okay, so for the first one, if we've got lambda1 is equal to 4, well, we need to work out our eigenvectors using this equation here. So we just need to write down A minus lambda1, which is 4, times by I, first of all. If we work this out, then we're going to have 1 minus 4, 2 minus 0, 3 minus 0, 2 minus 4, which can be simplified to -3, 2, 3, minus 2. So this here would just be equivalent to our matrix M. We can note as well that this second row here, if we call this row R2, is just equal to minus our first row R1. So that means that if we take A minus 4i times by our eigenvector, which we don't know yet, so it's called VI, that's just going to equal minus 3, 2, 3, minus 2, which we found on the row above, times by our eigenvector. So let's just, for argument's sake, call the elements of this x and y. This is just a linear system of equations, right? So we know that this has to be equal to 0 because we've got this equal to the 0 vector up here. So this must equal 0, or we must have minus 3x plus 2y is equal to 0, and 3x minus 2y is equal to 0. Okay, so that's just converting that matrix equation back to a linear system of equations. So any eigenvector that satisfies these equations will work. And what we can do is we can do a swap here by noticing that, okay, well, if we set x to be equal to this value, and I've just highlighted in yellow, and we set y to be equal to be minus the other value, then we're always going to end up with 0. Okay, and that will work for both equations. So for example, if we set, I can change this to being V1. So this is not VI, this should be a V1. So we can set V1 to be equal to 2 and minus 3, so 3. And that is an eigenvector for the system. So like I said, all I've done here is I've set the x component to be equal to the coefficient for the y term in my equation, and then I've set the y component to be equal to minus the x term. It doesn't matter if I'd used them the other way around. As long as I switch those coefficients around and take one of them as being negative for the other one, then it would still work. Okay, so if I check this, if I do a times by a minus lambda I, so a minus 4i times by v1, that's going to give me minus 6 plus 6, 6 minus 6, which is just equal to 0 vector. So this checks out because I did a minus lambda I times by vi, so lambda I here was our eigenvalue 4, and this eigenvector is what we found here, this v1. Take that, we need that to be equal to 0 because we want this equation here to hold. And so this eigenvector that I found satisfies that equation. Okay, so as long as we, finding the eigenvectors can seem a little bit tricky at first, but as long as you choose values these values here, we could choose any multiple of this. I could have chosen 4, 6, for example, and that still would have satisfied these equations. As long as I choose values that satisfy these equations, then we can work out what our, as long as you choose one, you can choose the other one, basically. So we just need to make sure that our eigenvector is chosen to be a multiple of 2, 3 in this case. Okay, what about for the second eigenvalue? So, I said we had to do one of the eigenvalues first, find the eigenvector associated with the eigenvalue, and then for the second eigenvalue, we need to find its associated eigenvector. So here we're going to have a minus lambda I. So here we're going to have a minus lambda 2 times I, which is just going to be a plus I, because lambda 2 here is minus 1. So that's going to be equal to 2, 2, 3, 3. And again, here we see that this second row is a multiple, in fact, 3 over 2 times by the first row. So we always end up in a case like this where one of our rows is a multiple of the other row. So we can, again, solve these equations by setting a plus I times our eigenvector v2 equal to 0. So we can take, in this case, v2 is equal to, well, if I use the same swapping rule as I used above, I'll take this value here, that would have been equivalent to my y component above. So I'll take that as my x component. So that's going to be 2, and then I'll take minus the coefficient that I had in front of what would have been my x component, so minus 2 in this case. So minus 2. Again, I could choose any multiple here of this, and that is still an eigenvector. Okay, so we could have had 2 minus 2, I could have had 3 minus 3, for example, if I'd gone by the second row of this matrix, or I could have had 1 minus 1. It doesn't matter. The reason being that because we have a times by our eigenvector is equal to some scalar times by that eigenvector, by definition of it being an eigenvector associated with that eigenvalue, all that's happening is that you are stretching along, you're scaling along that vector, which is your eigenvector. So it doesn't matter which you choose as being your eigenvector, you're just stretching along in that direction. So we can choose any value as long as we sit along that eigenvector. Okay, so any non-zero multiple will do. Okay, so to summarize, I've been talking about eigenvalues and eigenvectors in a quite abstract way, about how we can find them and how they relate geometrically to movements of a vector. And that is quite an abstract way of thinking about things. What you really need to know is, okay, how do I calculate my eigenvalues and eigenvectors? And what's the interpretation of that? Okay, and if we go all the way back to the beginning, just briefly, the reason we care about these things is because, say, if we've got a population model that's in this form here, so suppose y is our population in the next year and x is the population in the first year, we want to say what happens to our population as we keep applying this matrix to it. So that matrix is just, say, describing births and deaths and individuals maturing from being juvenile to being adults. What happens in the long term to this population? Okay, and our eigenvalues and our eigenvectors tell us what's happening to the population. So if we can find those eigenvalues and eigenvectors, then we can work out what is going to happen to this population. Okay, so that's why we care about them. So just think of that in your mind, that it's always about long-term behavior when you think about eigenvalues and eigenvectors. A few things to note. So that we can only have eigenvalues and eigenvectors for square matrices. That's because we need to find the determinant of them. We of the matrices, that is. And if we want to find eigenvalues for our matrix A, then we need to find the roots of what's called the characteristic equation of determinant of A minus lambda times I. And lambda here is our set of eigenvalues. Okay, so lambda I would be each of our eigenvalues. So this will give us a polynomial in lambda. So this gives us a polynomial in lambda, which we can then solve. In the case of a 2 by 2 matrix, you just have a quadratic equation, which you should be able to solve. Solve that for lambda, and that will give you 2 values of lambda. Okay, and for each lambda I, we then can work out its associated eigenvector. So remember that each eigenvalue has an eigenvector associated with it. And for a 2 by 2 system, you'll always have 2 eigenvalues and 2 eigenvectors. And that satisfies this equation here. So when we pair our eigenvalue with our eigenvector, then we are able to solve this equation here. And if we have 2 by 2 problems, then we can always write them in this form for our eigenvectors. Okay, so if we, as you saw up here, we ended up with a matrix. I'll just highlight this. These matrices here, when we did A minus lambda I, we ended up with one row being a multiple of the other one. Okay, so we always end up in this sort of situation here. And so we can always write down a solution with x is equal to m2 here, so this coefficient, and y is equal to minus m1. Okay, we could have done minus m2, excuse me, we could have done minus m2 and y is equal to m1. It doesn't matter because we can take any multiple that we want to. So those are the basic facts about eigenvalues and eigenvectors. You should go back and review this material if you're not quite clear on them. Make sure you know the distinction between an eigenvalue, which is a scalar, and an eigenvector, which is always associated with a particular eigenvalue. And that is obviously an eigenvector is a vector. Make sure you know what the characteristic equation is of a matrix and have a go at solving this. You can just write down a matrix of your choice and then work out what the characteristic equation is and how you can calculate your eigenvalues and eigenvectors from that. And there's also some study questions here as well. Okay, thanks very much. Bye.